Okay, in the last video, we saw how we can connect circular motion and universal gravitation for objects that are in satellite motion. So let's review that really quick. We know for a satellite that the strength of the gravitational force between the satellite and the object it's orbiting, which we'll call the Earth in this example, is proportional to g, the mass of the satellite, the mass of the Earth, and the orbital radius squared. Well, we also know that in a satellite, F sub g is a centripetal force, which is equal to the mass of the satellite times the centripetal acceleration, which is mv squared over r. So when we replace this, this becomes a centripetal force, which becomes mv squared over r. This is good to do every time because deriving this expression becomes an important skill for you to be able to learn for these types of problems. We see that 1r cancels, the mass cancels, and we were left with, at the end of the last video, v squared g, mass of the Earth, over r. So to find an expression for the linear speed, all we have to do is square root this. So you'll see often the linear speed of a satellite. Now remember, this is for satellites only because satellites are the objects that are moving in a circular path in orbit due to the force of gravity. So that's a specific condition for satellites. That equals the square root of g, the mass of the object that's being orbited, which in this case is the Earth, but you can change this to the moon, to the sun, whatever object it is that's being orbited, divided by the orbital radius. So this expression can be used for solving for the linear speed of a satellite in orbit. Now, what if we wanted to solve for the period of a satellite in orbit? Well, here we have to break down and see what v can be re-expressed as. Okay? Because we know that from circular motion, the linear speed of an object in circular motion is equal to 2 pi times the radius over the period. So now we want to try to substitute this in and then get an expression for t. So I'm going to replace v with 2 pi r over t. And to get rid of our square root sign, I'm just going to square both sides. So I get g, mass of the Earth, over the radius. So I have a radius squared here. 4 pi squared r squared over t squared is equal to g, mass of the Earth, over r. So now let's get all the t's over on one side. So I'm going to multiply both sides by t squared. And then I want to get, so that's to get the t out of the denominator. Now I want to get the g and the m and the r on the other side. So let's do this in a different color. I'm going to multiply by r. So I multiply by another r. I'm going to divide by mass of the Earth. So I divide by mass of the Earth. And then I'm going to divide by g. So divide by g. And it looks kind of messy, but let's re-express this over here. So I get t squared on one side is equal to, and I'm left over here with 4 pi squared r squared times r, which is 4 pi squared r cubed, divided by, and then I'm left with the mass of the Earth times g, the universal constant. And I can square root both sides, and you'll get that t is square root of 4 pi squared r cubed over the mass of the Earth times g. Now there's a bunch of different ways you can express this. You can pull out the 4 as a 2. You can pull out the 4 pi squared as 2 pi. Sometimes you'll see it like this, like 2 pi square root of r cubed over mass of the Earth times g. Or sometimes you might see this as r to the 3/2. However you want to do the algebra from there. But this is how we can take the expression for linear speed, write it as 2 pi r over t, And the same r, is the orbital radius, is the same r here, it's the same r throughout, and then express this in terms of the period. So two useful conversions when you're solving problems for satellites.